Yes, sir.
Okay, great. So this is week 2. I mean the second week in which linear regression is being described in more detail, and further how we are going to take care of nonlinear relationship of data that exists between features and label, and that is how to make your model more complex and more powerful, and at the same time how we can make sure that our complexity is not increased to the extent that our data is is overfitted. That brings up the next topic, which is regularization. So the focus of this entire week was on these two topics, which is polynomial regression and regularization. Okay, so before we begin, anybody would like to ask any questions, any queries, share any thoughts? Okay, then let's begin. Okay, I hope my screen is visible. Is my screen visible?
Yes.
Okay, great. So let's go to our first set of activity questions. So the first question says, which of the following is are correct regarding polynomial regression? So polynomial regression is a regression algorithm that models the relationship between label and features as kth degree polynomial. That is okay. That what do you think, is it true or false? Hello, am I audible?
Yes, sir.
Yes. So anybody would like to take a guess at this? Option A.
It is true.
It is true, right? And that's the very definition of polynomial regression, that we are going to take kth degree of features. Next option is the order of polynomial model is kept as high as possible. This is a bit interesting. What do you think of this one?
No, it should not be too high, not be too low.
Exactly. So the option suggests that make it as high as possible. I mean, make it 100, 200,000 or something. But no, in practice, that is not what we do. Third option is polynomial models can be used to approximate a complex non-linear relationship. What do you think of this?
Yes, it can. It is true.
Yes, it is. Yes.
Can
Go ahead.
be. It's written as a can be, so it's not suitable. So it can be.
Yes. So I think polynomial models can be used to approximate a complex non-linear relationship. So in the video, if you remember, if I remember correctly, what happens is sir had explained an example in which the data points look like they are forming a sine curve, just one period of it. So, and in order to fit the model onto that data, we are actually using polynomial regression. So I think this option is true. The data used in polynomial regression for training is of linear nature. What do you think of this?
No, it's false.
No, then it won't be a polynomial.
Right.
Yes.
We need to take the feature and we need to convert in the number of degree. Then only become as an X polynomial, you can say, as a feature.
Exactly. So for if the data is of linear nature, then we don't need polynomial transformation at all, right? So therefore, this option is false. Let's go to question number 2. If the relationship between study and explanatory variables is curvilinear, then which of the following would be better ML model? Okay. So it says that assume there is a non-linear relationship between features and label, and then choose the best of the 4 options. Okay. So first option is linear regression without polynomial transformation. What do you think of this?
No. That means it doesn't have any degree at all.
Definitely. So this is going to be false, right?
Yes.
Polynomial. What about option number 2?
2 is a single degree. That means it's like a linear.
It's like linear only.
Yes, exactly. So one in option A and B are same. Okay. What about option number C?
Yes,
Yes, C is correct.
Yes, C is correct. Right. Because since the relationship between x and y are non-linear, we can definitely go with polynomial transformation and then fit a model. Sounds good. Yes. Okay. Question number 3. Which of the following is our polynomial regression equations? What do you think of first one?
yes, sir. It's a polynomial at least
Of degree?
of degree 1.
That is true. What about option B?
It's multivariable.
Right. But is it a polynomial regression equation?
Yes, sir.
Right. What is the degree?
One only. One for all.
Yes, exactly. And what about third option?
Yes, sir. It's a polynomial.
And what is the degree?
N or n plus 1.
Yeah, it's a polynomial. It's a degree of you can say n.
Exactly. This is degree n.
N.
Because the highest power term is at the last, which is bn multiplied x raised to the power n. Right. Therefore, it's one feature, but degree is n. So this is to be true also.
So one question. See, here we are considering even the degree is 1 as a polynomial, correct? But in the question we are not considering. Okay.
So in
exam, the question will come.
Okay.
If both the options are there, then it will become a confusing whether we need to consider as a degree 1 as a polynomial. Of course, in normal mathematics, even degree 1 we get telling as a single monomial we are telling.
Right. Right. So thank you for suggestion. We will make sure that this kind of confusion is not there in the exam. You're right. So question number 3 is more likely, about a mathematical perspective, that every polynomial, so all 3 of them are actually polynomial expressions. And that's why we chose all 3. Yes.
So I'm confused. Like in one of the questions, it said if the degree is 1, it was linear regression, and here we are saying it is polynomial regression. Why is it?
Well, I understand your point. Polynomial regression is kind of a superset of linear regression. So it involves linear regression also. If you set degree k is equal to 1, then it becomes linear regression. I mean, conceptually, polynomial regression is also a type of linear regression because the features are, added linearly. They are the solution is taken by taking linear combinations of features.
Okay, sir. I mean, it makes sense mathematically, but to differentiate linear regression, not polynomial equation and linear equation, polynomial regression and linear regression, we are using a notion of k being, if it is equal to 1, we say that it is linear regression, right? So then only the third option should be correct, I think, for this one, because we are using polynomial regression here in the third question instead of polynomial equation.
Okay. So I see your point and I understand your point of view. I think the problem is in the wording of this question. So if it would have been written properly like polynomial equation, then it would have made sense. But regression, polynomial regression, okay, you are taking that k is always greater than 1.
Yes, sir. Otherwise, we cannot differentiate between linear regression and polynomial regression.
That we can say now the polynomial regression is linear regression with polynomial transformation. So it can be taken as a just for degree 1 we are not using polynomial transformation, else we are doing like similar things for it.
Yes, yes. So I think, that is a better way of to see this. K is greater than equal to 1. It is polynomial regression. See, it is still a linear regression. Even the last equation, even we are taking nth degree of feature vector, we are still, computing linear combinations of all those polynomial powers of x. So it is still linear regression conceptually. So I think this question is okay. Maybe the wording should be changed in either question number 1 or somewhere else, or it should be explicitly mentioned that k is greater than 1 or 2 or something like that. Then I think there should be no confusion.
Yes, sir. Yes, sir. You are correct.
Yeah. All right. Does that answer your question? I mean, I accept that there is a bit of confusion. I mean, conflicting expressions in the questions. We'll try to make sure that this is avoided. Okay.
Sure, sir.
Sure. All right. Let's go to question number 4. How do we generally choose the best polynomial degree to overcome underfitting as well as overfitting? Okay, that is a great question. So what we want to do is we want to choose the best polynomial degree. We don't want to underfit the data, neither we want to overfit it. So the options are by calculating RMSE and then plot the degree versus RMSE plot. Okay. Second option is by calculating validation RMSE and then plotting degree versus RMSE plot. Third option is both of them, and fourth option is neither of them. Okay. Anybody would like to take a guess on this?
Yeah, it's actually both.
Both of them.
Then only we can compare.
Exactly. Because if we, keep increasing the degree, the training RMSE plot is going to decrease slowly.
Yeah.
Right? It will be a decreasing plot. And but the validation RMSE, it will, it will go to a minimum value, and after a value of degree, it will keep increasing because the model is actually overfitting. And therefore, what we want to do is we want to figure out a value of degree in which training and validation losses, both of them are small, not just one. So right answer is both A and B. Okay, question number 5. Which of the following are true about polynomial regression? Higher degree polynomials are generally prone to underfitting compared to lower degree polynomials. What do you think? Is it true or false?
No, sir. The opposite is true.
Exactly. So this is false. As we increase degree of the polynomial, the capacity of the model increases. Okay. So it is likely to remove underfitting. It is not going to be prone to underfitting. Option number 2 is higher degree polynomials are generally prone to overfitting compared to lower degree polynomials. Okay, this we just discussed. Option number 3, lower degree polynomials are generally prone to underfitting compared to the higher degree polynomials. I think this is just the negation of option B. What do you think?
Yeah, correct. It's just reverse.
Right? Yes. So this has to be true also. Option number 4 is high degree models generally fit well on training data, but predict poorly on validation data. What do you think of this?
Yes,
It's
sir.
also
This is
true.
the definition of overfitting.
Correct.
Exactly. So this should also be true. Let's check our answers. And all of our answers are correct. All right, let's go to next activity. Question number 1. Overfitting is caused by assigning higher weight to the higher order polynomial terms, whether it is true or false.
Swanim?
Yes.
Regarding the last question, the three or four options that we discussed, in
Okay.
the first two options, there is a explicit statement whether it is the model is underfitting or overfitting, right?
We are talking about this question, right?
Yeah, this question.
Okay.
In the option number 2 and 3, the nature of fitting is described, right? Whether it is overfitting or underfitting. Then
Yes.
based on that, we can say that whether it is due to so there is a comparison between higher and lower here,
Yes.
right?
Yes. Exactly.
Whereas in
Yes.
case of fourth option, higher
Mhm.
degree polynomials generally fit well on training data, but
Yes.
predict poorly on validation data. This is not correct, right? Because there we do not know what kind of model, I mean, what kind of data we are, in what background we are actually making this statement.
Okay. Okay.
If the data is, if the the target model is nonlinear,
Mhm.
then higher degree polynomial will fit well, right?
Okay. Okay. So let's say our generating function was of degree 2. That is we are that is we are using a parabolic function to generate our data points. Okay. Then we fit a degree of 10 model to it.
Correct.
So
That part.
yeah.
When now you are making an assumption that it is degree 2. Let's say I
Yes.
have a degree 11 9 or degree 10 polynomial which I'm
Yes.
trying to
Yes.
fit. So in that
Yes.
case, it fits well with training data, right?
Right. Right.
And
So in
also
option
predicts well with validation data.
for training data, it will fit well. Degree 2 generating function and 10 is the model's degree. It will
No,
fit on training data.
compared to linear model, it is still a higher degree model, right? When the
Right. Right.
so the predict poorly on validation data may not be correct, isn't it?
It's told that generally
It's
higher degree
generally,
model,
yeah. What
not
is generally?
always.
Yeah, not always. Generally, they are written.
Generally, it said, but
Mhm.
we do not know what kind of data we are talking about.
No,
So how
if
can
if
we
you
make an assumption?
if you consider like that normal, whenever you are going a higher degree, the training is going, the model is going to remember or learn each and every point. That means it's always going to be a loss zero. But in the same case, when you put in validation data, because it's learning the point by point. So validation data, there is a chances of error. Of course, you can contradict the question. Yeah.
No, my point is we do not know anything about the data. So how
Mhm.
can we make a statement that generally higher degree polynomials won't fit for validation data?
Okay. Okay. So for the option number 4, I think the intention of that sentence is you can go as high as possible. I mean, you have a large range of degree. So for in that case, let's say even if we fix that the degree of our data is 100. So the generating function in our data set was a polynomial of degree 100. But what happens if we fit the model of degree 109 or 150 or 200? So something like that. The
No, no,
intention of this option is that.
yeah, that see, when I was answering this question, my intention was not to make any assumption about the data. So then
I see.
obviously I did not select the fourth one. Now when you select it, when you want to make this statement true, then you can put an argument saying that okay, if this is the case, then this will happen, right?
Okay,
So
so let's say we don't know the degree of the data, but it must have some certain number. It cannot be infinite. So assume any number like k. Okay, so k is the degree of the generating function in the for the data set.
Mhm.
Then what happens if we fit a model of k plus 2 degree
No, compared to linear, it is still higher degree, right? Even if
compared to
k is, even if let's say k is 4, k is 5, k is 6, compared to
okay,
linear, it is still higher degree, right?
right?
So higher degree, anything more than, let's say, maybe you can say anything more than 1 is a higher degree.
Yes.
So you cannot say for if the underlying data is 2 degree, you cannot make a statement that higher degree polynomial is going to overfit, right? Maybe it will
That's
fit
why it's
properly.
saying generally in the question. If you start from 0 or take it to 1000, then generally the higher degree models will be overfitting.
Yeah, so the intention of this question, the option is as you increase the degree of the model, when you are fitting on training data, it is likely you'll observe this, that it fits well on training data but performs poorly on validation data.
Okay.
Hello.
So
Sir, another example for this is like the output of linear regression label is continuous, but it can be discrete also. So generally it is continuous. That's what this is also in the same line.
So discrete numbers are, subset of real numbers. That's fine. I understand your point that we are not making any assumptions of the data. Still, we are not making any assumptions of data. So it's an activity question. So is this? I hope this was explained properly in the video. Do you think it's not, it was not?
I understand the concept of overfitting and underfitting very well. Like, for example, if you look at the introduction to statistical learning textbook, I don't know if you had got a chance. So there they would compare three models, right? So overfitting is different in the is explained in the context of the data set. If the underlying is a linear, let's say single degree polynomial, then overfitting definition, the degree, the capacity of the model at which overfitting happens is at the lower end. If it is if underlying data is already polynomial, let's say 9th degree or 10th degree, then the overfitting happens to the rightmost spectrum of the capacity, right? It is like it is variable. So the higher degree is a subjective term. It is like even 2 is a higher, 3 is a higher, 4 is higher, depending upon the data.
Okay.
So it is subjective question is what I'm saying. It is subject to what kind of training data you have in your hand.
Right. So I think the intention is fulfilled. So you already know when it starts to overfit. So maybe we can rephrase this option so that there is no confusion. But now, but once we explain, okay, assume that k is the degree of the data and k plus 1 is the degree of the model that you want to fit, or any model which is more than k degree, then I think the option
probably
for
as we go towards higher degrees of model, then generally the training data fits well and prediction validation data doesn't fit well. Maybe that is a correct statement, right?
Yes,
I mean, unambiguous statement. I don't want to say correct or incorrect, but unambiguous and ambiguous.
Yes, definitely. Okay. So now let's go to, I'll try to make sure that this option is changed. Okay, now let's go to second set of activity questions. Overfitting is caused by assigning higher weight to the higher order polynomial terms. Okay, what do you think of this?
It's true.
It is true. Anybody would like to take a guess at why is it true?
But sir, in the tutorials, it was higher weight both on the negative side and the positive side. So the question could have been absolute higher weight.
I see. Okay, so again, I think I see. So you're saying that minus 100 has lower weight and plus 50 has higher weight?
I'm not saying that. The question is forcing me to say that. I mean, it would have been better.
Okay. See, so when we are talking about the weight, any weight parameter, any coefficient of any feature, the higher weight means the absolute value of the weight.
Okay.
So minus 100 has greater weight than 50.
All right.
The reason for that is, yes.
Yeah, I think negative sign only indicates whether it is positively correlated or negatively correlated.
Right. Yes.
So weight is actually is what the size magnitude of the weight is what we consider, right?
Exactly.
That determines the sensitivity of the.
Yes, absolutely.
Relevant parameters. Okay.
Yes. Okay. Let's go to the next question. Overfitting can be solved by which of the following ways? First option is by increasing the size of the training set. What do you think of this?
Yeah, this is correct.
Yes, correct.
By increasing the size of the training set.
Yes. What do you think of option 2? It's just the opposite of first, so it
opposite.
has to be false. What about option number 3?
That is not correct. We have to decrease the complexity of the model.
Yes. Yes, we have to decrease the complexity of the model. This way it will not overfit. Yes. Question number 3. L2 regularization is also called lasso, ridge, elastinate, or not? Yes, the correct answer is ridge.
Ridge.
Okay. Question number 4. Which of the following is correct expression to update weight vector W in k plus 1th iteration of gradient descent algorithm?
Yeah, first option.
First option, definitely. Second, there's a plus sign. Third, there's 1 by alpha. Fourth also has 1 by alpha and plus. So first has to be the right one. Okay, question number 5. Which of the following is true about a model as the regularization rate lambda increases? The model overfits the data, the model underfits the data, or no effect on the model capacity? Which one do you think is the right one?
Underfits the data.
Underfits.
Underfits the data. Absolutely right.
The coefficients will become 0.
Absolutely, yes. Question number 6. In lasso regression, penalty term contains first norm of the weight vector, second norm of the weight vector.
First norm.
That's right. Question number 7. Which of the following is the penalty term in ridge regression?
Second norm.
Second norm of the weight vector. Overfitting is more likely when you have a huge amount of data to train.
False.
Yes, absolutely false. This is so this is something we already covered in one of the questions. Where did it go? This one. Right? Overfitting can be fixed by increasing the size of the training set. So of course, if we are using huge amount of data, our model is not going to overfit. Let's check the answers. All of them are right. Any questions so far?
No, I think
okay. Okay, let's go to the next set.
Sir, I had a general question about this.
Yes, yes, please.
Why does regularization work?
Why does regularization work? So to understand that, you will have to understand why does overfitting happen if we increase the degree of polynomial.
Okay, but how does regularization control the overfitting, reduces the overfitting?
Yeah, so you tell me how increasing the polynomial degree causes overfitting.
It tries to memorize all the instances literally, and
okay, but mathematically what is happening? That what you're saying is absolutely right. Mathematically what is happening? What is happening to the coefficients of the features?
The coefficient of the features.
Yes.
They are scaling up and down erratically.
The curve is scaling up and down.
I mean, they are taking erratic values just to fit the data with the training. That's okay. What I learned from the tutorials, but I didn't understand why adding that extra term would stop that from happening.
Yeah, sure. That's a very valid point. So let me rephrase. Let me say a statement about the weight vectors of the polynomial. If the degree is too large, when the overfitting happens, the individual weight parameters are going to take larger values as compared to a smaller degree polynomial. Do you agree with this statement?
Yes.
Right. So what is happening is, as the value of each individual weight vector increases, okay, so what it is more prone to fluctuate. Fluctuate means it has more capacity to, as you mentioned, go up and down.
Okay.
Okay. So this is what we have to avoid. We have to make sure that the weights of the features are not too large. They don't have a large magnitude. If we are successful in avoiding this, then we have found a way to reduce overfitting. Do you agree?
Yes.
Okay, fantastic. At this point, now what we do in the loss function, we add this penalty term. Penalty term is basically the magnitude of weight parameters. As soon as it starts to our model starts to overfit the data, the values of the individual weight parameters go high. Okay, and the loss function also goes higher. So this is counterintuitive, right? This is not what we wanted. So what happens is the gradient descent does not go into the direction where the overfitting is happening. It goes into the opposite direction.
Okay, so we are forcing the gradient descent algorithm to find a solution where not only the loss function is low, but also the weights are low.
Absolutely right. They are not very large. We can control that with that lambda parameter.
Oh, it's like that we are adding constraints like they are Lagrangian. I think. I think constraint optimization. It's kind of constraint optimization that we learned in machine learning foundation. Isn't that a correct assumption?
Constrained optimization. I'll have to look at that. What exact definition that is?
Yeah, I think it is correct. It is constraint optimization in the sense like we are trying to put a condition on the space in which the betas are the weight vector is located. So we are saying that it is only in the distance space of this one. What do you call the magnitude
are
of
not explicitly mentioned.
But constants are not putting in the
Like
objective function. We need to put as a separate condition.
By adding that extra term, we are forcing the loss function. We are forcing the gradient descent algorithm to only look for solutions where W is not too large, and for all the solutions where loss function is small but the W's are large, those solutions we are discarding by adding that extra term. Isn't that the correct way of surmising this?
Yes, summary is okay. I'm not sure about the constraint terms. See, for constraint, do we, for example, let's say we want to put a constraint like
regularization parameter is just preventing from the coefficients to get very large.
Right.
But from the explicit constraint point of view, there is no explicit constraint that the weight should be below specified some constant.
Value. Yes.
Like we learned in machine learning fundamentals.
Yeah,
right.
That's true. Okay, I understood the gist of it. Thank you.
Okay, great.
So I have a related question.
Yes.
Why is lasso regression more aggressive than the ridge regression? Is it because of the fall in modulus? Is it because it falls faster than the square function?
Whether it falls faster than the which context you are saying this?
Like in the lectures when lasso and ridge regressions were explained, like we also saw that it smoothens out faster. Like use of the lasso regression it makes it smoothen faster than ridge regression.
Okay, I would say yes, that is true. But I'll have to get back to you about the mathematical reasoning about this.
Okay, sure.
Yeah. Can you please post this on discourse?
Yeah, I will.
Okay, thank you.
I think those are how much aggressively you want to punish the coefficients getting excessive. So if you want higher aggressiveness or higher penalty for way more excessive coefficients, you go for higher penalty.
So
but
I think our question is
the same. Lasso will lead to a faster reduction or smoothening of the function as compared to ridge. Because of the way the penalty and the function is defined, the regression is defined.
I think it is not about smoothness. I think with lasso, the probability of the constants, the coefficients becoming zero is high. Like in case of ridge, we can only guarantee that the size of the coefficients will be smaller. They don't just blow away like the case where there is no penalty applied. Whereas in case of lasso, because of that absolute constraint that we have in the first norm, the probability of getting the coefficients to zero is high. So in case of lasso, we will get most of the coefficients zero. Where in case of ridge, the values will be smaller. They may be nearer to zero, but they may not be zero.
I got that, but I think I still have that question. I'll post it because since modulus is not differentiable, it's not very easy to see like why the fall is faster. I think. I mean, that was more of my doubt.
So one of the explanations I found is, let's say if it is the second norm, if you imagine the weight space, the second norm is like a it's like a sphere at the center.
Right.
Okay.
Yeah.
It has a smoother surface.
Right.
So whereas the weight space is a contour. Remember in the first week there were these contours, right?
Yeah.
So these contours can touch this sphere at any point. So whereas in case of lasso is like a let's say the absolute value, the function is like it is sharp at the corners, right?
Right.
On the axis, it will be the corners are on the axis, like it's like a rhomboid, and these rhomboid corners are on the axis. So when the contour touches this absolute equation, I mean absolute surface, it can touch only at the points on which it can touch on the points where these points are lying on one of these axes.
Got it.
So then it becomes the corresponding other coefficients have become zero. Whereas in case of Euclidean space, it is in case of sphere, the ridge regression, it is a smoother surface, so it can touch at any point. So it is not necessary that the coefficients should be zero.
Okay. Got it.
That is the reason.
Visually. Okay. Thank you.
All right. That was a good explanation. I'll look deeper into this. Now let's go to next set of questions, which is 3.3. Which of the following code snippets returns a polynomial transformation of second degree on the feature matrix X? Feature matrix X has 3 samples and only 1 feature. Okay, this is a this is different question for some time now. So this has a code snippet in it. Anybody would like to take a guess on this?
This will be third option because we are taking the second degree.
Right. So what we are doing is in all the 3 options we have a function called polynomial transform, and inside that we are concatenating columns. So the first option, it concatenates a column vector of size 3, which has all ones, and the feature vector X underscore. In the next one is also exactly the same. It is doing exactly the same thing. The third one is now we have 3 column vectors. First one is the dummy variable. The second one is X itself. And the third one is X raised to the power 2. I think so. Third one should be the right one.
I have a question here, Swarnim.
Yes.
So this here is said that it's a feature. Can you just scroll up, please?
Sure.
It says this feature matrix, right?
Okay.
There are multiple features in the matrix, right? So if it is second degree, in the lecture also it was said that if it is x1, x2, then there will be one x1, x2, then x1, x2 also, x1 into x2 also.
Okay.
As a polynomial transformation, that is not there in this any of the codes, right?
Right. So what is specifically mentioned is the size of this matrix. It has 3 samples and only 1 feature.
Oh, okay, okay. Though it was mentioned as feature matrix
Yeah,
there.
right, right.
Oh, it said only one feature.
So it's a special case of feature matrix where we have only one feature, not more than one.
Oh, okay. One feature is fine. Okay, thanks.
Yeah. Okay. Let's go to question number 2. Another name for an output attribute is predictor, independent, transformed, and dependent.
Dependent.
So dependent.
Dependent. Right. Predictor is another name for feature. Independent is also the same thing. Transformed variable, we can have the labels as well as features transformed. So this is not decisive. The only option is dependent variable. Okay, so for question number 3 and 4, let's say you have a data set D and you design a polynomial regression model of degree n. And you found that training and testing error are very close to 0, which means it perfectly fits the data. Great. What will happen if you fit a degree n-1 polynomial in this regression model? I think this is very close to what we discussed in activity 3.1, some around the last question.
It will underfit. No?
Exactly, it is going to underfit. What will happen when you fit a degree of a polynomial model of degree n+1? Question number 4.
Yeah, it will overfit.
It will overfit the data. Yes. Okay.
But if you see in some cases, even if you are increasing the degree like from 3, 5, 6, 7, some of the 3, 4, 5, 6, 7, all are to be a constant. Okay. Even the as saying like in some example, if you see that 5 to 7, it is same. So if you go that contents, then if the option suppose it will be there that the whether the test and train can be 0, then which one we have to select?
Okay, if test and train are 0 for degree n, see, again, it is mentioned that it is likely to overfit the data.
Okay, okay, likely. Okay, okay.
Yes. So likely is, likely takes care of these absolute cases. Like whether it will increase or not, we don't say that, but it is likely, yes. It is definitely not decrease. It will definitely not underfit, right?
Okay, 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 yeah, right.
Also, if I may ask one more thing here, the learning curves that we discussed in the lecture, right? So the learning curve we would draw between the degree of the polynomial and the cross validation error, right?
Degree of the polynomial and
cross validation error, and whichever is the lowest degree at which we are getting the lowest error, that is the degree that we're going to choose.
The cross validation, yes. So cross validation error, yes, I remember it correctly. So the degree that we choose is the no degree for choosing the best degree. We plotted this RMSE plot versus degree, right? Training and validation
against the loss.
Yes.
That is the cross validation error. There is a diagram in the lecture slide also.
Okay.
So there was a force.
It has both errors for training as well as validation set, and it formed a convex graph, I think. So there is an optimized degree you could achieve.
Okay, maybe I was confusing with lambda there, probably.
Yeah, so let's hold on to that question. When that curve comes in, that plots lambda versus loss function, then we'll take a look at that. Okay.
Yeah, sure.
Yeah. All right. Let's move on to next one.
I have one more general question. Like, should I save it for the end, or I can ask now?
If it is related to something we are discussing, go ahead.
Yeah. So, like, when do we choose to reduce the degree of the polynomial versus using a regularization rate?
Okay, that's a good question. So that's what you're asking is something. How would you actually fit a model which has proper polynomial degree as well as regularization rate, right?
No, my question is, suppose I'm trying to fit the model and I get that I see that it's overfitted. How do I decide whether I want to reduce the degree of the polynomial or I want to use a regularization term itself?
Okay, good point. So what you can do is take a higher degree polynomial rather than reducing the degree. Introduce the regularization. I mean, let's say that generating function has degree 3 and your 4-degrey polynomial is actually overfitting the data. Now you have two options: either you can reduce it to 3 or you can reduce polynomial regularization.
Right.
So what is going to happen is, let's say regularization, if you introduce and you try out different values of lambda, you'll find that, you know, after introducing regularization, you look at the coefficients of your weight vector, then or the features, then you will find that the degree 4 terms are going to get very small amount of magnitude in weight.
Okay. Okay.
So yeah, so experimentally you can figure, you can see this, and this way you can deduce that, okay, these polynomial features and so degree 4 polynomial features are not required.
Okay. Okay. Got it.
Yeah.
Fine.
Sir,
Thank
can
you.
I add to that?
Sure.
Yes. So in machine learning, there is generally a trade-off between interpretability and accuracy. So in case we go for a linear model or a very simple model, we can have higher interpretability. So let's say we have 4 features and we have 4 coefficients. How much does each feature contribute to our target variable? That can be ascertained when we want interpretability. And if we, let's say, go for a deep neural network or any other higher complexity model, it loses out on interpretability. So as far as business analytics is concerned, if we want how much our target variable is influenced by one particular model, we will go with regularization of the model, so that we know how much each feature contributes to our target variable. But if we want let's say higher accuracy, we can go with higher degrees, so we can have polynomial features, and then we just care about the accuracy. We don't want how much coefficient each feature has and how much it contributes.
Okay, okay, got it. So similar thought process I can apply to lasso versus ridge also, right? Like whether I want all the features or whether I want to eliminate some of them.
Yes, yes, sure.
Okay, okay, got it. Thank you. Thanks.
Yeah. Okay, let's go to the next set of questions.
Sir,
yes.
So lasso is also used for feature selection in a way, right?
Lasso is used for feature selection. I wouldn't say that. You could use it. I mean, definitely. See, lasso and that, both of them, lasso or ridge, they are going to give you a weight vector, and based on the weight vector, you can decide which features you want to keep or which features you want to remove. So in that way, yes, you can use both.
Okay, sir. Thank you.
Yeah. All right. Should we move on to the next set of questions? All right. So the first question is, which of the following is best suited to test the linear relationship for dependent and independent continuous variables? Okay, which one do you think should be the right answer?
Scatter plot.
Scatter plot. Yeah.
Right, absolutely. Question number 2, polynomial regression is used for which of the following cases? Relatively small number of samples, classify binary data, third is handle non-linear data. Which one of these is suitable case for polynomial regression?
The third one.
I think third one.
Yes, absolutely right. Second is classification. That is just not the problem we are solving. First one is relatively small number of samples. If we use that apply polynomial regression on a small number of data points, we are going to definitely get overfitting. So third one is the best one. As the degree of polynomial transformation increases, what happens to the training error? Great. This is a good question. It is going to decrease, increase, or it is going to stay the same?
It'll decrease.
It will decrease, yes. Because the model's capacity is going to increase, it will more likely, as the degree of polynomial transformation increases, it is more likely to remember the data points, and therefore the value of training error will decrease. Next question. Increase in the degree of polynomial leads to?
Second option.
Just the opposite of what we saw in the previous question. Oh, not the opposite, actually.
One question.
Yes.
Right.
Right. So it is being asked, the same thing is being asked in different manner. So if degree of polynomial transformation increases in question number 3, we are asking what will happen to training error. And the question number 4 asks what will happen to the complexity of the model. Definitely it is going to increase. Therefore, the training error is decreasing. Question number 5, which of the following is true about polynomial regression? A small change in input will result in small change in output. A large change in input will result in small change in output. A small change in input will result in large change in the output. Which one do you think should be the right one?
Because small change in input will result in
third option. Yes.
Yeah, because we are increasing the power and power.
Yes, and due to that, overfitting will start to creep in, and because of that, the weight parameters, the coefficients of the features are going to take larger values, and they are going to contribute into larger fluctuations, even if there are a small change in input. Therefore, option 3 is right.
Sir, can you go to third number question once again?
Okay, question number 3, this one.
Yeah, suppose here you have put some hints like the training size is more or larger. In that case, we can say it likely to be same, right? Because when the number of size of training size increase, even you have the degree is more, it is not going to be, the training error is not going to be reduced too much, correct? It can more and more, correct?
So, theoretically, let's say you have 100 data points, or it could be millions or billions also, that's fine. But for example, you have 100 data points. So you can create a model just by looking at the data points without fitting regression or doing anything. You can create a model which gives you training error of 0.
Even if the number of size is millions, you can say that if you increase.
Yes, theoretically, you can create a model right away, which is going to give you training error 0. So basically, all data points will become the root of the polynomial.
Okay, got it. Thank you.
Yeah.
Sir, I have a question here. Should I wait till the end or ask now? It's
Sure,
a general question about polynomial regression.
Okay.
The question is why we are only considering exponents from 1 onwards. Why we are not considering negative integer exponents? Because sometimes there are relationship which is inversely proportional. Let's say we don't know the actual relationship between, we don't know the expression for gravitational pull, and now we have to derive it. And we have this input for mass of the first body, mass of the second body, and distance r between them.
Okay.
But the actual intrinsic relationship is that it is inversely proportional to the square of the distance. So r would have an exponent of -2, but our polynomial regression would have no hope of deriving that, because we are only considering exponents from 0 onwards, or sorry, 1 onwards.
Okay.
Why is the reason we are discarding negative exponents?
So first of all, how many features do you have in this model?
Okay, let's
M1,
say
M2 and R, right?
yes, M1, M2 and R.
And the relationship between them is linear or not?
No, I want to the response variable. I mean, the target variable is the force between them, and somehow we have empirically, or we have experimented and acquired some training data where we know the gravitational pull between objects when the distance is this and the mass of the first body and second body is this. Now I want to derive the expression. Let's assume that we live in a universe where we don't know that expression that Newton came up with.
I see. For the exact problem that you're posing, I think it does make sense to create another feature which is 1 by r, and then creating the transformation. Okay, so for this kind of problem, you are not taking actually, to port this or cast this problem into linear regression, what you want to figure out is if there is any feature which is inversely related, right? Which is your distance r.
Yes.
So in that case, what you can do is you will have to create another feature which is inverse of distance, and then create polynomial applied polynomial transformation to that particular feature or set of features, and then observe the and then fit the model. This way you can figure it out, but it's intuitive. Typically we don't see problems like this in when you are trying to model for example the amount of loan to be given, or what should be the price of the house and things like that. But yeah, you couldn't do it. That's not an issue.
So what you are saying, we would not consider the distance between them, but we would rather introduce another metric which should represent the closeness between them.
Exactly.
So that will be the inverse of the distance.
Yes.
Okay.
Definitely you can do that. Yeah.
Okay. That might work. Yes.
Okay.
Thank you, sir.
Yeah. All right. Let's move on to the next set of questions. Okay. So this question is actually repeating. Ridge uses which knob? I think it is L2. We can quickly skip this one. The different ways to tackle the problem of overfitting are, I think we have seen this one also. No, there's something new. Train with more data, we have seen this one. We have also seen regularization part. We have a discussion about this. So these two are the correct answers. Train with less data is going to have the opposite effect. Add a constant term to the loss. This is not going to do anything, because adding a constant, it will be absorbed in the bias term. Okay, let's go to question number 3. Which of the following are correct about regularization? It leads to change in the linear regression loss function, which in turn results in change of gradient calculation. Second, it is a technique used to reduce the errors by fitting the function appropriately on the given training set and avoid overfitting. Okay. Third option is it increases the errors by fitting the function appropriately on the given training set and avoid overfitting. Option 4 is lambda is a hyperparameter known as regularization constant and it is greater than 0. Okay. Which one do you think of 4 of these, out of 4 of these, are the correct options?
One is correct.
It leads to change in the linear regression loss function. That is true.
Second one.
It is a technique used to reduce the errors by fitting the function appropriately on the given training set and avoid overfitting. That is also true.
And the fourth one.
And the fourth one is lambda is a hyperparameter. Yes. Great. Can you tell me, so one quick question, one side question. Do you think degree in polynomial regression, is it a hyperparameter or not? It's an open question. Anybody would can take. Yes.
It's an hyperparameter because you should decide that how much you can say curvilinear you are going to be taking.
Exactly. Exactly. You know, any parameter which is not part of your model is hyperparameter. So lambda and degree k, they are not going to be part of your weight vector, and therefore they are hyperparameters. Question number 4, loss function after implementing regression is, which one do you think is the right one?
First one. Yes, first one.
Okay. So last two options, you can see that this W multiplied by W, that's not even possible. Because both of W is a column vector, so you have to transform it. So only one of first one or option A and B could be right, and in option B, this transform operation is missing right after first parenthesis. Therefore, the correct one is 1. Yes. Question number 5. Gradient function after implementing ridge regression is
The first one.
Yes, that is the right one. No, first one cannot be right. XW minus W.
I'm sorry. The last one. I'm sorry.
Last two.
Last option. Question number 6. Normal equation after fitting with. So what is the solution, of regression problem if you use ridge regression and you use normal equation method?
C.
It's third option. Transpose plus lambda here.
Yeah. It could be first or third. Okay, yes, it is third one. See, let's eliminate the other three options. This is not possible. This is only possible if the feature matrix is square. And for all problems, it is not going to be there. So this is going to lead to an invalid multiplication of two matrices. Same over here. Right, so therefore, this is also not true. For this one, X and Y, they will have there will be discrepancy between shapes of the matrices. So the third one remains. Okay. All right. All answers are right. Let's move on. .6 is done. 3.8. Ridge regression calculates loss function as this. Then what is true about first term and the first part and the second part? Okay. So I believe the first part is up to here and the second part is the penalty term. All right. Let's read the options. First part of the equation gives rise to elliptical contours centered around the linear regression least square error solution. Okay. Second part of the equation represents a circle. All right. Third option is second part of the equation gives rise to the elliptical contours. Okay. And the fourth option is first part of the equation represents a circle. So basically what we have to figure out is which one is circle and which one is solution to linear least square problem and creates ellipse. Okay, which one do you think are the correct options?
Ellipse and circle, is
it? So you're asking what is this ellipse and what is the circle?
Yeah, I'm guessing the first one is ellipse.
Yes, that is right. That will create elliptical contours.
Circle as per lecture.
Yes.
Yeah, the second option is circle.
Yes, absolutely. Right. So these two options should be right. Okay.
But my question is that if you read the circle equation, that is something like x square plus y square less than greater than 1. Okay. But here we have just w square. I know sir has explained, and in the graph it is also coming in circle, but how it is plotting circle?
Right. So see, W transpose W is going to give you W1 square plus W2 square, right? And so this is a circle which is going to be centered at the origin.
Oh, okay, center at the origin.
Right.
Okay. Okay.
Yeah.
Thank you.
Sure. So, for trying to see how does it form circles,
Yes,
you'll
sir.
have to,
Even I didn't get it.
okay, for to understand how does it create circles or circular shapes, you'll have to imagine a 3D space in which X and Y, W1 and W2, and on Z axis you have this term W transpose W, which is the loss. Okay. Hello.
But sir, W1 and W2 need not be the same, no? In which case it will be
Absolutely,
3D
they don't
ellipse.
have to be same. They don't have to be same.
Then won't it become a 3D ellipse of sorts?
No, it will become a bowl shape, which is, its lowest tip is sitting at the origin.
Okay, I can't imagine.
Okay, let me see if I can draw some figure quickly. Okay, can you see this screen?
Yeah.
Yes, sir.
Okay, so let's say we have this 3D model. This is my X, this is my Y, this is my Z, or in other words, this is my W0, this is my W2, and here I'll write P, which is equivalent to the penalty term. Okay, so now let's say so our penalty term is basically W0 square plus W2 square multiplied by some constant. So for now I'm including that regularization rate. This is what we have, not W2, W1. All right. Now W0 and W1 can take any value. That is right. For now, let's say they take some value which is constant. For sake of explanation, I'm going to do this. So let's say if it is 0, what is going to happen? We are going to get a point 0, 0, 0, which is over here at the origin. Do you agree?
Yes, right.
Great. Now let's say it could have let's say its value is 1. Of course, it can have some value between 0 and 1. But for the sake of demonstration, let's say it is 1. Okay. Now what will happen is we are going to get if we solve this problem, 0 square is equal to 1 on a 2D plane, like x square plus y square is equal to 1. So what kind of equation we are going to get?
So 0, 1 or 1, 0?
0, 1 and 1, 0 are going to be 2 points. What equation is this? What kind of shape is this?
The circle.
Circle with radius?
Radius 1.
Exactly right. So what we are going to do is, so x square plus y square, this is for all the values such that the sum of x square and y square is going to be 1. We are going to get a circle with radius 1, and it will be now this is our penalty term. So this is equal to P, right, which is on z axis. So we are going to get a circle with height 1. It will be parallel to our xy plane, and its height will be 1. All the height of every point on this circle will be 1 because it satisfies this equation.
Now we got it. Okay. After that, the function will come and it will try to touch the point, and we will get the different W0, W1, W. Okay.
Exactly. So let's say if I put, instead of 1, I could have put 2. Now this time if I put 2, what will happen is I'll get a circle with the radius 2, right? Or this basically becomes my penalty weight of my penalty term, or the magnitude of my penalty term. So it will be another larger circle, and its distance, the distance of all the points on the circle with xy plane will be 2, and this is how it will look like. So if I keep increasing, if I plot for all values from 0 and it increases slowly and slowly, I'll start to get larger circles which are centered at origin and parallel to xy plane. So now if I want to plot this into a 2D plot, this is how it will look like. They are not absolute circles, but I hope you understand this.
Yes, sir. Thank you.
Does it make sense?
Yeah, I think you understood. No, it's clear.
Okay. All right. Let's move on to question number 2. Which of the following are correct about regularization rate in ridge regression? As it tends to infinity, the effect of regularization diminishes. As it tends to 0, the weight vector tends to 0. As it tends to 0, the solution is that of least square error. As it tends to infinite, we get a weight vector which is tending to 0. Which one do you think are correct answers?
Third and fourth one.
Yes, it's 10 to 0, then it's correct. Right, third.
Okay, so as regularization tends to 0, yes, the solution is like the original problem where there is no regularization. Option number 4, as tends to infinite, the weight vector tends to 0. That is also true.
Yeah.
Okay. Question number 3. Consider the following steps for ridge visualization. Generate or getting the data, obtain weight vector with different lambda, compute mean squared error and ridge regularization term, set up MASH grid. It shouldn't be MESH grid. It should be MASH grid of weight values. Draw contours of mean squared error and ridge regression constraints. Draw path of weight vector from least mean squared error value to the least value of ridge constraints. The correct order of the steps is. So this is a big question. So many things that you have to read and understand. Okay, which one do you think is the correct option? Any questions about this? It's all clear. So this question is actually getting into, if you were to create those visualizations explained in the video, how would you do it?
So setup mesh grid of weight values is initial. Is it the like what exactly does it mean?
So it means that when you are creating 3D plots or contour plots, you will have to and you have a function that you want to plot on that chart. You will have to set up a MASH grid. I mean a set of values of X and Y pairs.
Okay, fine.
Right. Okay, I think the third one should be the right one. What is the fourth? Yeah, this is the subset of match grid and compute mean squared error and ridge regression. That's, yes, that makes sense. So step number 3 has to happen after step number 4. Okay, we'll see the answer if it is right or wrong. Let's go to question number 4. Which of the following are correct about lambda in ridge regression for solution path? Okay, as lambda tends to infinite, the solution moves closer to the least penalty point. Okay, as it tends to 0, the solution moves closer to the least error point of loss function. Okay, as it tends to 0, the solution is the solution of least square. As it tends to infinite, the solution is at the center of the circle, which is a 0 vector. Okay, which one do you think is are the correct options?
It should be B and D, right?
No,
It should be.
C is definitely correct. If
C is
lambda is
correct.
0, then solution is least square error.
Yeah, that is true. If lambda is 0, then there is no regularization, right? Option number 2, as it tends to 0, the solution moves closer to the least error point of the loss function. But now, since the loss function has that a penalty term also, then it is not going to be true.
But the
No, that's
penalty
where
point
we're
will
saying
become 0, no? Penalty term will become 0.
yeah, yeah.
So yeah, this will be true. B will be true.
So as penalty lambda tends to 0. Okay, this is slightly ambiguous, I would say, because in that case, if we see it that way, option B and C will become same.
Yeah, but it, like, we are saying as it tends to 0, right?
Yes,
So
yes.
then wouldn't it be B?
The loss function. Okay, the solution moves closer to the least error point of the loss function. I think this option B is a bit confusing. This is not clearly written.
There is no uncertainty about it, right? B tells that it only tends to gets closer to error point. It is not definite, but actually it is definite. If lambda is 0, then it is
It
least square
doesn't say
error.
it is 0. It says it tends to 0.
Correct. So it actually it is same solution as the least square error. So when it says it tends to 0, then the statement is a little it says it's not sure, right?
Yeah, that's what I said earlier, right? If we see it this way, then option B and C are equal.
Okay. Okay.
The loss function is our penalty term plus the original loss function.
Yeah, I think B should be then correct. Because it
Right.
says it is not 0. It says it tends to 0.
Okay, the solution moves to closer to the least error point of the loss function. I think then there's no need for option C, right? Option B and C are same then.
No, option C doesn't say lambda is 0. It says it tends to 0.
Option B and C, both of them say it tends to 0, right?
No. For C to be correct, lambda has to be 0. It is not tending to 0, right? It's not the question of tending to 0. If lambda is 0, then solution is least square error solution.
Okay. I think this is another example of not properly written sentence.
Yeah, I think it's in context of the visualizations.
Yes,
so
yes.
Then it makes more sense. If you just look at it as standalone statements, they may be confusing. But if we see the pictures, then I think it's what it's trying to say.
Yes, right. So I think for this one, either B or C, and least penalty points. Option A.
Okay.
D should be right.
Yeah.
Let's see.
But what does least penalty point here mean?
Least penalty point means when the lambda multiplied by W transpose W becomes least, which is 0.
Okay.
No penalty.
Yeah.
Got it. Okay.
Okay. Question number 5. Which of the following are correct about lambda in lasso regression? As it tends to, I think this is very similar to previous question. As it tends to infinity, the solution is the center of polytope, which is 0 vector. Option number 2 is if it tends to 0, the solution is at the center of circle, which is 0 vector. Option number 3, as lambda tends to 0, the solution is the solution of least square. Option number 4, as it tends to infinite, the solution is at the center of the circle, which is a 0 vector.
So lambda tends to 0, or that option should be same in 4 and 5. Whereas
exactly,
we do not see option B here.
yes,
Okay.
yes. I think for this one, this should be right. C is definitely correct. If there's no regularization, that the solutions of that least square, that is fine. As it tends to infinite, the solution is at the center of the polytope, which is vector 0. I think this should be right, because if we are regularizing too much, then there is no scope for W to vary, and the solution is going to become closer and closer to 0. Yes. Question number 6. Lasso function calculates loss function as, okay, then what do the first part and the second part of the equation represent? Okay.
Second part is polytope. We already discussed, and I think this is
yes. Second part of the equation represents a polytope. First part represents
elliptical contour center.
exactly. All right, let's see the answer of this question. I think I made just everything opposite.
No, this is the B and C confusion.
Right, B and C confusion is okay, but D, it says the D answer is the right one. No, first one is right. Okay.
A is correct, and then B or D or C.
As it tends to 0.
Yeah, it's B and C. It's confusing actually.
You're right. You're right.
Yeah.
Okay. Okay. Definitely B and C. They seem very, very similar. There is no semantic difference. Okay. I think we got this. We covered this. We analyzed this. One of them should be right. Okay. It's fine. I'll make sure that this confusion is removed from the options. All right, let's move on to next set of questions. All right, in case of multi-output regression, there are more than one output labels, all of which may or may not be real numbers. There are exactly two output labels. There is exactly one output label, which is a real number. There are more than one output labels, all of which are real numbers. Okay.
Yeah, last one.
The first one is the right one.
Last one.
Last, not first.
Are all
Last.
real numbers.
Yes, last one. Question number 2. Which of the following is our example of multi-output regression? Predicting number of gold, silver, and bronze medals won by different countries in the upcoming Olympic Games. Okay, fantastic. So, can you tell me what will be the, how many output variables we are trying to predict in this problem?
3.
Exactly. Number of gold medals, number of silver medals, and number of bronze medals. So this is going to be an output, multi-output regression problem. Option number B, predicting goals scored by Cristiano Ronaldo in the next 10 matches.
Yeah, it's also true. You're predicting 10 outputs. Yeah.
Exactly. Question number 3. Predicting total runs scored by Indian team in upcoming India versus South Africa cricket match.
No, it's a single output.
Yes, it's a single output. Option number 4. Average rainfall in next 3 days.
Also
Yeah, 3
multi
numbers.
3 numbers.
Yeah, this is multi-output.
Right. Question number 3. In a data set, there are P number of instances, Q number of independent features, R number of dependent variables, then total number of weight vectors will be. Which should be the right answer?
R. Third option R.
Exactly. Can somebody explain to me?
Yeah. As we are telling about R dependent variable, that means we have R different levels, multi-outputs.
Exactly.
And for every level, we should have one set of it. So as we have different levels, we should have R different set of weights.
Absolutely right. Yes. Moving on to next question. Question number 4. A multi-label regression problem with K output can also be solved with K independent single label regression problems. Is it true or is it false?
True.
It's true.
Okay. So let's take one example quickly. Let's talk about this predicting number of gold, silver, and bronze medals. So instead of posing this problem as 3 output variable problem, what we can do is we can create 3 single label regression problems, right? One will predict number of gold medals. The second one will predict number of silver medals, and third one will predict number of bronze medals. So yes, the answer should be true. Let's check the answers. I think yes, all of them are right. Questions so far? Okay. Let's move on to the practice part. Let's take a look at the theoretical practice questions first, then we'll go to programming questions. Okay, this is an interesting question. Rahul observed a set of training and validation root mean squared error values while fitting linear regression models on non-linear sample data by applying polynomial transformation of different degrees. Okay, so in this table we have 3 columns. One is the degree, second is training error, the third one is validation error. Now let's go to question number 1. The linear regression model with blank degree polynomial underfits the data. Okay, so which of the 3, 0, 1 or 2, if we take a polynomial of degree 0, 1 or 2, which of these is going to underfit the data? Can you tell me by looking at this chart?
It looks degree 0 because both are error is very, very high.
The errors are high, so degree 0 is going to underfit. Great.
Second one, we cannot take underfit because training is low where the validation is high.
Training error is low, but the validation error is high. Is that what you're saying?
Yes.
But you can see for degree 0, train error is actually higher than validation error.
Yeah, it's fine.
Anybody else would like to take a guess at this?
Yeah, I think see initially, so training error is continuously falling.
Okay, great.
Whereas validation error is falling for some time and until degree 4,
Okay,
and then it is increasing.
good, very,
So
very good observation.
so degree 4 is the maybe apt. So 0, 1, 2 will be underfitting, because 3
Absolutely
is also underfitting actually. I think you didn't give 3 as an option. So
right.
0, 1, 2, all of them will be underfitting.
Absolutely right. Yes. So the crux of this problem is to identify the pattern in the validation error. So you'll see a bowl-like shape in 2D chart. So it will keep increasing from 0 to 4, and after 4, it will for 5, 6, 7, and 8. The validation error is actually increasing. So the best value for this, the best value of degree to deduce from this chart is degree 4. So anything below that is actually underfitting, and anything above that is actually overfitting. So 0, 1, 2, all three options are going to give you a model of less capacity and therefore underfitting. Question number 2, the linear regression model with degree blank polynomial overfits the data 6, 7, and 8. So we have options 6, 7, and 8.
Yeah, same thing. When be above 4, everything will overfit.
Exactly. So you can see that, for degree 4, error is 0.24, for degree 5, 0.43. So as we increase the degree, it is actually giving us higher validation error. For 6, 7, and 8, the same pattern continues. By increasing degree, validation error is increasing, and therefore 6, 7, and 8, all three degree values, the model is going to overfit. Option C. The linear regression model with degree blank polynomial smoothly fits the data. Which one is the right answer?
4.
4. That means option B. Okay. Question number 4. So all these questions 1, 2, 3, they are simply reduced by the table. So in order to answer that, it's good to remember that all we have to do is figure out the pattern which exists between the validation error and training error. Question number 4. Consider feature vector x 1, 3 after applying third degree polynomial transformation. Which of the following is the corresponding polynomial feature vector? Okay. Anybody would like to take a shot at answering this?
Yeah, one is a dummy. We have to add one dummy, and after that x1 and x2, that is 1, 1, 3. Then 1 square is 1. 3 square is 9, and 1 into 3 is 9. Option 3.
Option 3. Okay. Anybody else?
So
Option
3. So degree 3. It has to be at least 20.
Oh, degree 3. Okay.
So degree 3, not 2.
I think it's option 2.
Yeah, it's option 2. Yeah, 1.
Sir,
Yes.
it is 1, 1, 3, which is of degree 1. Then 1 square, 1 into 3, and 3 square, that is degree 2. Then 1 cube, 3 cube, 1 square into 3, and 1 into 3 square.
Absolutely right.
So that fits option 2, I think.
Right. You're absolutely right. Option 2 is the right answer. Option 4 you can discard right away because the highest degree is what? Highest value is 81, which is 3 raised to the power 4. So this is definitely not going to give you the answer because degree, this can happen only if required degree is 4, but we have 3. So option 4 is gone. Option 1 and 3 are also gone in similar manner. So for third degree, the highest value should be 3 raised to power 3, which is 27. So 1 and 3 both are gone, and by the explanation that you mentioned, which is very apt, option 2 should be the right answer. Okay, let's go to question number 5. Observe the data points X and label Y plotted in the screenshot given below. Which of the following model will best fit these points? Classic linear regression, okay, polynomial regression with degree 3, or polynomial regression of degree 6 with regularization rate 0.5.
Degree 3.
Degree 3, right.
Because we cannot be so specific about lambda is equal to 0.5 from the scatter plot.
Yes, you're right. And anyways, it looks like a sinusoidal curve for only one period.
Yeah, right.
Question number 6 and 7 have common data. Consider the feature matrix X and corresponding label Y in the below table. For this data, assume regularization rate as 0.01 and compute ridge regression loss and lasso regression loss using weights which are given below. Which model gives the minimum loss? Okay, for this, it will require us to make some computations. Do you want me to do this?
Yeah, we can do together maybe.
Okay, sounds great. So now I'm going to switch to my other application. Please help me with the numbers. Okay. So we have X and Y. So what are X? Can you tell me?
1.1.
1.1.
I'm telling column first, rows first, okay? I mean
Okay.
columns.
Column first, okay.
1.1, 1.2, 2.3, 1.5, 2.9, 2.3.
Is that what you're saying?
No, it's actually 2 by 3. So 1.1, 1.2 is one column.
I see.
2.3, 1.5 is another column.
3 cross 2.
Okay.
Yeah, sorry. No, 2 cross 3, right? 2 rows and 3 columns.
Let me see.
3 rows, 2 columns. 3 cross 2.
It is 3 rows, 2 columns.
3 rows, 2 columns.
So 1.1 and 1.2 are in same row. Goes here. One 0.6 and 1.2. So this is a table that we have. Okay. And we have 2 weight vectors also, one for ridge and one for lasso. 0.5 minus 0.5, 1 minus 0.3. 1 minus 0.3. So I think this stands for W ridge and this one is for lasso. Okay, sounds great. So for before we go, we have to write the definition or equation for loss function, which looks something like this:
half into
half of
x transpose w
xw minus y transpose
xw
minus y, and depending upon the penalty, so penalty could be ridge or lasso. If it is ridge, it is going to be lambda by 2 weight vector transpose w, or it could be lambda by 2 w first now. Okay, so let's calculate this one. This is going to be common for both of them. No, not common, sorry. So let's calculate this for ridge first. So basically, what we are doing is we are subtracting the second term from the first term and dividing it by half for ridge. Okay, so let's solve the ridge problem. So xw minus y, if we calculate it, this will turn out to be minus 0.05, 0.4, 0.3. Is this calculation correct? Hello?
Yes, sir.
minus 0.1 yeah,
Minus 0.1.
by 2, right? Minus points.
Yeah, so right now I have not multiplied anything. It is just this quantity.
Okay, yeah, I think -1 we need to do, right? Minus y.
Minus y. Yes, definitely. Sorry. So -1, minus 0.6, minus 1.2. Thank you for correcting me. So this should come out to be minus 1.05. This will be minus 0.2. This should be minus 0.9. Is this correct now? All right. Now what we have to do is, in order to calculate this quantity, we will have to take a square of every term and add those.
1.05 square is 2.1.
Okay.
Sorry. Wait.
105. It will be like 25, 110, something like this. 4 values. So it will come out something like this, right?
1.9525 I got.
1.9525
9525 total.
Oh, total by adding all of these terms.
Yes.
1.9525.
9525.
Okay.
Divided by 2.
Yeah. So so this quantity is xw minus y transpose xw minus y multiplied by. Okay, this is this quantity. Great. So in order to divide multiplied by get this first quantity original value, we'll have to divide this by 2 and we'll get 0.97625. Is that right?
Yes, that's correct.
Okay, great. So this is the quantity that we created. So first half of the ridge problem is done. The second half of the problem is this. So we'll have to do calculate the second norm of vector, this vector, weight vector. So this will turn out to be, I think, 0.5 divided by 2.
Yeah.
Okay. At any point of time, if you think that I'm making a mistake or going fast, just let me know.
Into lambda.
So this will this
into lambda, right? 0.25 into lambda.
Yes, 0.25 into lambda. And what is our lambda?
0.01.
0.01. So this will turn out to be 0.97625 plus 0.0025. Right? How okay. So this will be 57879. Is this correct?
1.00125.
1.00.
No, correct. Wait, I think I made a mistake. Are there 0.1, right? I think only 1 0 is there. 0.25 into
0.01.
0.1. Okay. Yeah.
You said 0.01, right?
Correct.
Let me check.
0.01.
Okay, then this should be right, right?
Yeah, that's correct.
Okay, so this is the value for 1/2 of the problem. Okay, so we have solved it for ridge. Now we have to solve it for lasso also. Okay, same method we are going to do. So 1 minus 0.3. Okay, this one is going to be a bit trickier.
So normal one will be 0. First norm will be 0, right?
Of which one?
Oh, this is another weight vector. Sorry. Okay.
Yeah, this is another weight vector.
0.7.
So this entire calculation, let me mark it. This is what we did for ridge. Let's do the same set of calculations for lasso. So maybe I should copy these. No,
So 0.97625 will be same.
Pardon me?
The least square part will be same, right?
No, it will not be same. The vector is changed now.
Oh, W is changed.
Right? This is the one. Okay. So we can ignore this part now. Is everybody following, or do you want me to go quickly and just solve it or leave it? Because the calculation will follow in similar manner.
You can leave it. I think we can.
Okay. Everybody agrees with this?
Yes.
Okay, sure. So the calculation of I'll just go run through it quickly. xw minus y. This calculation transpose xw minus y. This calculation is very similar to what we did for ridge regression. The only part that is going to change is the norm 1. So it will become 1 plus modulo of 0.3. Lambda is 0.01 divided by 2. So this is the only place where the method of calculation is changing. Apart from that, everything is the same. Okay. Here's my window. Okay. Now let's go to question number 8, 9, and 10. Given below is the code snippet used for generating combinations of polynomial features. What is the output of code shown below? Okay, this is a good one. So in this one, getting combinations of feature matrix X of degree. The variable name is also degree. Okay. Anybody would like to answer this one? Hello.
Yeah, it will be 1, 1, 1, 2, 2, 2, because we have the 2 degree.
1, 1, 1, 2.
1, 2, and the 2, 2.
Okay, that is there for option 1 and option 2. They are there. But what about the label?
Okay, it's multiplication. Second option, 1 into 2 is 2, not 3.
Right.
1 into 1, 1, 1 into 2, 2 into 2, 4. Yeah.
Yes, that's the correct one. Question number 9. What is the output of the code shown below? Who would like to answer this one?
Option 3. 4, 4, 4, 4, 4, 5, 4, 5, 5, 5, 5, 5. Yeah.
Option number 3, you are saying?
Yeah.
Okay. Yeah, I think it is right. So, do you have any confusion how these terms are coming up? Or you're okay with this?
So it'll be nice if you could just briefly explain.
Sure. See, get combination. So the method that we are defining is get combinations. X is your feature matrix, okay, or feature vector, and degree is your the power up to which you want the polynomial features.
Okay.
In question number 8, the degree is 2, okay, and the input feature matrix is 1, 2. So we have to create combinations of degree 1 and degree 2 with this feature vector 1, 2. So you will see that if we take 1 square, we are going to get 1. And how we are defining that? See this one. Every time we are computing a new feature, how we are going to do that? We are going to multiply them. Okay. X comma y. These are two features. How we are going to get the new feature? By multiplying them. Okay. So 1, 1, what the feature, what the value we are going to get? 1, 1, 2, we are going to get 2. For 2, 2, we are going to get degree, the value 4. Similarly, here the degree is 3. Okay, and the input feature vector is 4, 5. So 4 cube, we are going to get something like this. For 5 cube, we are going to get something like this. And the value of that feature will be 120, because we are multiplying to get the answer. So the answer should be 125. For when the feature vector is 4 only, all 3 of them are 4, then the answer should be 64. Then the other combination that we could create is 4, 4, 5 and 4, 5, 5. And therefore the third option seems to be right one.
Okay, sir.
All right. Question number 10. I think somebody mentioned about something like this in the when we were discussing about the activity questions earlier.
Yeah, correct.
Yeah. Question number 10. Ram trained a ridge regression model with various regularization rate, lambda, values for some data by cross-validation procedure, and selected a best lambda by plotting the cross-validation errors as given in the chart below. from the above chart, which lambda value did RAM select as the best regularization rate for the model to smoothly fit the data? Okay, which one do you think is the right answer?
Is it 10 to the power minus 3?
Absolutely right. Because, and can you tell me why is that so?
Because cross-validation error is minimum and after that it's rising.
Absolutely right. So the correct answer should be 0.001. Next question, state true or false?
I
Yes.
have a general question.
Yes.
So lambda is a hyperparameter, right? So
Yes.
why don't we use the cross-validation error for selection of the learning rate? Because learning rate is also a hyperparameter, isn't it?
It is definitely a hyperparameter. However,
because
see,
there in week 2, when we said we were only taking the fixed proportion, right? 80, we were dividing the data into 80-20 portions, and we were repeatedly fitting the data on the training set. We were not using the cross validation there.
Okay. Yes.
So can't we use cross validation for determining the learning rate?
I would say no, because it will be grossly inefficient. So see, the objective of finding a good value for lambda and good value for alpha, which is learning rate, are different, right? For lambda, which is the regularization rate, it is going to be part of the final predictions. So so keeping everything else same, we say that the learning, the training is another procedure. We are just focusing on, for this chart, we are just focusing on, let's say you take care of the training, then if you take for multiple values of lambda, which what best cross validation error you get, right? And there when we are choosing the learning rate, our objective is to make sure that we are going in the right direction at the right speed for training. We are not thinking about we are not taking care of whether our model is performing well on the test case or not, or the validation set or not, right?
Okay, you mean to say it's a hyperparameter, but it is not a model parameter.
Alpha, right?
Learning rate, yeah.
Absolutely, yes.
So wherever model parameters are there, then we do cross validation, use cross validation.
Yes, yes, absolutely.
Okay.
Question number 11. State true or false. The number of elements in the weight vector for polynomial regression model corresponds to the degree of the polynomial used for transformation. Is it true or false?
Yeah, it's true.
Yes, it is true. Question number 12. Given below are code snippets of different loss function. What is the question? Choose the correct statement from the following. Okay, great. Linear regression loss function, lasso regression loss, ridge regression loss. Okay, so what we have to do is we have to identify which piece of code is doing what. Which one of them is a plain loss function? Which one of these are lasso and ridge? Can anybody tell me which one is plain and which one is lasso or ridge?
The second one is lasso because we are taking the regularization rate half into temp one.
Second one is lasso.
Yeah, we are adding this regularization rate, right?
Yeah, we are adding regularization rate, but my question is whether it is lasso or ridge.
Second one is ridge. Temp is the that
Sorry,
XW
temp is
minus
that is
Y
correct.
transpose.
It's a ridge, right, sorry.
Yes, yes.
W
It's
transpose
one
W.
okay.
Absolutely right. So temp 1 is actually the quantity representing the variable which represents W transpose W.
Yeah, right.
Right, and that belongs to ridge regression. Okay, so first one, there is no this is a plain loss, and the second one is ridge loss. So let's see which one is the right one. I think second should be the right one.
Yeah, right. Lasso is not there in the.
Oh, lasso is not there at all. Yes. Question number 13. Lasso regression. Choose the correct statement. Lasso regression assigns sparse weights. That is, it assigns non-zero weights to only important features and zero weights to unimportant features. Ridge regression can be used if there are several features that are useless. Okay. The penalty term added to lasso loss function is absolute value of the magnitude of the weight, and ridge lasso function is squared norm of weight.
Yes, third one is correct.
Is correct. Yeah.
Okay, third one is correct. What about the first two?
Yeah, first also lasso create sparse weight. Number of zeros they are assigning to the weight. This is okay.
Yes, that's also true.
Not sure about whether useless or not.
Features are useless.
If it is not assigning any weight, doesn't mean the features are useless.
No, ridge regression in principle we use when weights are more, not.
Sorry, okay, it's ridge, not loss. Sorry, yeah.
Yeah, right. We want to use it only when the weights are of large numbers. It's not because the features are uses. It is not like we do not have any view on whether a feature is useful or not. The procedure itself is figuring out which one is having
useful
more
or useless.
Yeah.
So ridge regression can be useful. So there is nothing like ridge regression is, providing any points against this in a situation where there are several useless features. So I think it should not be included. Yes, I think our analysis was right. Anything which we made mistake on, I think only this one. So what was the mistake? The number of elements in weight vector for polynomial regression model corresponds to the degree of polynomial used for transformation.
Sorry, it's wrong. Yeah, I told wrong. Because it's multiply here, right? Sorry, it should be false.
No, I think number of features.
Yeah, number of
features in polynomial regression corresponds to degree.
Right,
not number of elements in weight vector. I think that's
absolutely right. Yes. So this should be false.
Yeah. It's actually.
We are still doing something wrong. I think there's one question. Okay, for this one.
Calculations. I think.
Yeah, calculation we have not done. Yeah,
not this. All right.
It's 2 marks gone.
Sir, in the last problem, I didn't understand the explanation for not choosing the second one.
Okay, so the second option says that ridge regression is very useful if in the data set there are useless features. Okay.
Yes, sir.
So there is nothing like that. That ridge regression has any advantageous inherent advantage in such situation. You can use lasso and ridge, both of them. So both of them are regularization techniques, and in general, if there are useless features in the data set, you apply the model, a regression model, whether polynomial or polynomial model with k greater than 1, or k or linear regression model just k equal to 1. After fitting the model, you can analyze the weights the weight vector and then figure out whether you have useless features or not. So ridge regression has no inherent advantage in this situation.
But both regularization techniques do help eliminate the useless features, right?
No, both of them are regularization techniques. They tend to provide you a technique to remove overfitting.
Okay, okay, so this does not have much to do with how important a feature is.
Exactly. Even without ridge regression, you can assign. I won't say how effective that technique would be, but if the model, if the data is linear, if you just without polynomial regression, sorry, without any regularization, if you choose the right degree, there are certain cases in which you will get the training and validation errors 0, and you can assign and figure out which features are useless and which features are useful.
Okay, and how did we do that?
Okay, so let's say we get a model like 5x plus sorry, let's say we have two features and the weights come out to be 10 and the second weight comes out to be 0.02.
Okay.
Okay, so which feature has higher magnitude of weight associated with it?
The first one.
First one, right? So in this way, we can say that the first feature affects the output
More
by a
than.
greater extent as compared to the second one. And this way we can say, okay, first one is very useful and the second one is useless. Comparatively.
Okay, just basis the magnitude of weight.
Exactly.
Okay. Thank you, sir.
Sure. So any one of you is taking ML practices also?
I don't have ML practices.
I see. So when you will take ML practices, you will have this specific assignment to figure out which features are useful and which are not.
RFE we are using, then backward and forward we are sequentially.
Exactly, yes.
Backward and forward, what?
Yeah, so don't worry about it at all. When you will read ML practices, you'll go through them. There will be proper assignment on this and an explanation.
It's a graded.
Yeah. So don't worry about it at all for now. All right, let's go to our programming questions. They must be already. Consider the input feature vector x. The shape of x is fixed 1/3. The degree of the polynomial is random number between 2 and 10. Write a function named polynomial transform, which takes the feature vector and degree of the polynomial as inputs and returns the transformed polynomial feature as the output as an NP array. Okay, so I think I have already written the answer to it. But without looking at the question, without looking at the code, solution code, do you have any queries about it? Did you face any problem when you tried to solve this one?
No, I did not attempt yet. Probably there are no questions.
Yeah, it is actually the way what we teach now in 2-3, the 1-1-1-2.
Yes, exactly. That question is has direct connection with this one.
Yeah, it's directly question.
Yeah. So, do you want me to show the code, or you would like to attempt it and then see how it works? And if have any problem, you can ask also.
Yeah, sure, we'll attempt.
Okay, I will be very happy. So, programming is something you learn only by doing it. Something which needs a practice. All right, and in one of the questions, activity questions, we also discussed the hint how to solve this one. Okay, let's go to practice question 2. Consider input feature matrix X, label Y, and weight W. The size of X, Y, and W are fixed. Okay, write a loss function named ridge loss to compute a ridge regression loss. This function should take the feature matrix X, the label vector Y, the weight vector W, and regularization rate, okay, as inputs, and it returns the loss value of the output. Note, add a dummy feature to X. Okay, so I think these are proper instructions.
Yeah, loss function is also in the practice assignment.
Yeah, also now you have put it in the pen and paper. It's the same thing. We need
Yes,
to
exactly.
same thing.
So I think by using this numpy array, we can quickly, there it is. I think it's trivial, nothing special about this one. So this is xw minus y, and this quantity is xw minus y transpose xw, and the second term is the penalty term. I think there is something missing. Can anybody guess what is missing from this one?
You have missed the regularization part.
Absolutely. So
No,
this
it's
has the
same
penalty
only.
term, but it does not have the lambda in it.
So it is 1 or lambda. I don't know. 1 by 2. What is this lambda? No,
It
it's
should have lambda in it. This is not 1. This is lambda.
okay.
Okay. I think that's it. Any questions so far about anything? Polynomial regression, some very interesting questions and explanations that we discussed today.
See, it is possible to say this ridge solution visualization that the circle and the contour.
Mm-hmm.
Share the code in the maybe in the discourse.
Okay, you would like to see how they are generated?
Yeah, we want to know that circle and what you teach in the board. Okay, I just want to draw it.
Sure. I'll make a note of this.
Yeah, thank you.
Okay, thank you everyone. You have been very supportive and patient.
One general question, Swarnim.
Yes.
How
Yes,
do we
yes.
put these visualizations into slide? Like professor was putting into the slide, and they were for various degrees, and even in
Okay.
last week the loss function was drawn, and it was like projected in different directions, right?
Okay.
So how can we do that ourselves?
Sure. So sir is using the matplotlib pyplot. That is the visualization library we are using, and for the computations he's using numpy. So you'll have to be you'll need one or two charts to get familiar with 2D and 3D charts, and once you are done it, you'll be very quick to learn it. For 3D charts, you will have to create mesh grids.
Okay.
XY grids. So for 3D charts, what you have to do is you have to create a set of pair points X, Y.
Correct.
And
But how do we take that into the into the slide and make it like there was this video where the degrees were changing, and the fits on different graphs.
I see. So that is actually an animation, and that is created from several plots that were created using Matplot.
Okay, even those animations can also be done through Matplotlib.
For that, what you will have to do is you will have to use a Matplotlib library to create different charts for varying degrees, save them in a folder or in any place, and then use another set of library to get that animation.
Okay. So but that is not matplotlib then. Some other library where we just create some kind of a animation file output and we just put that into the presentation.
Yes. So that's another library which takes
Okay.
set of images and concatenates together and creates an animation.
Okay. All right. Thank you.
Yeah, sure. All right. Thank you, everyone. Have a good day.
Thank you.
Happy learning.
Thank you.
Yeah. Thank you. Thanks for this session.
Yeah. Good day, all, and bye-bye.
Bye.